My name is Rachel Allard. I'm the Vice President of Marketing here at Resonant Link, and thank you all for joining us this morning. Our webinar is sure to be full of very technical, but to most of us, very exciting details about electrochemistry, wireless charging, and all the things that make medical devices run. So I'm going to take a little bit of time to go over some housekeeping items. I'm going to introduce our speakers and then kind of give you a sense of the flow for the webinar, and then we'll dive right in. So firstly, we have Gregg Bruce, Senior Director of Research and Development at Resonetics Medical Power. Gregg has spent his career at the forefront of implantable grade batteries and electrochemistry. He has experience with primary, single-use, and secondary rechargeable batteries, and he specializes in helping medical device companies understand the best batteries for their application. So all your battery questions will give you the battery expert, Gregg. He holds a PhD in chemistry from the University of Victoria, and his research on electrochemistry and implantable grade batteries is frequently cited.
Okay.
We also have Dr. Grayson Zulauf, CEO and co-founder of Resonant Link. Grayson builds people-first companies that create a healthier world. He focused his early career on tackling climate change through electrification, leading product at Motive, where he launched first evers in electric garbage trucks and school buses. After realizing the broader applications of better wireless charging, he co-founded Resonant Link to use fast, safe, and reliable wireless power to power health for all. As CEO, Grayson and the Resonant Link team have designed their charging into 28 different medical devices and launched a 20-minute wireless charger for implantable medical devices with the aim of eliminating battery replacement surgeries and drivelines forever. Grayson holds a PhD from Stanford in electrical engineering and has published 43 peer-reviewed publications and received over 1,000 citations and 3 IEEE Best Paper Awards. He's a former NSF fellow, a Forbes 30 Under 30 honoree, a NASA iTech Energy winner, and a Dial fellow, among other things. So again, thank you all for joining. Quick housekeeping. The flow of today's webinar is Gregg is going to give us an overview of medical device batteries. Then Grayson is going to give us an overview of charging for active implantables and what's new in that space. And then we're going to have lots of time for audience Q&A. We'll be using Zoom's Q&A feature today, so you should see it at the bottom of your screen. And if you can just type your questions into the Q&A box, we'll answer as many as possible live. And then if we run out of time, we'll follow up with you individually after. All attendees and registrants will also receive a recording of the webinar. So without further ado, I'm going to turn it over to Gregg Bruce to share his screen and talk about batteries.
You do not know what you've got yourself into because you're given 2 PhDs open forum to discuss whatever they want, which is not what Rachel thought she got herself into. I started in batteries 32 years ago. I've been with the same company for 32 years. It's had 9 different names, same location. So I'm writing my second thesis called Black Cat Batteries, which is a history of my career. All kidding aside, the next slide should be right there. There we go. So basically, this is a quick history of Resonetics and then Resonetics Medical Power. Resonetics started in 1987, but we really want to focus on the implantable market. Our first implantable cell was in 2000. We're going to go through this really quickly. In 2004, our cell was the first lithium ion implanted, and then we've had several implants since then, both lithium ion, lithium carbon monofluoride, and lithium manganese dioxide. Thionyl chloride has kind of gone the wayside. Since I've been in batteries for so long, I've seen the evolution of batteries where some have been supplanted due to their strengths or weaknesses, and some have taken to the forefront. So the ones that are really taken to the forefront now are lithium ion and lithium carbon monofluoride. So a brief introduction. A battery is a form of energy. It can be portable. It doesn't have to be. We have stationary batteries for solar energy. You can manufacture it in a variety of shapes. There's two different aspects of batteries. One is chemical, one is mechanical. If you get the chemistry right, you can put it into any shape, any size, within limitations, obviously. But if you get the chemistry wrong, you're in deep trouble. It's a live manufactured part. You've got to remember that you cannot store it in the drawer with all the cutlery and expect the battery to be the same if you've shorted it with your knives and forks. You don't store it at high temperature. Universally, the worst thing you can do for a battery is store it at high temperature. It just ages a lot quicker. That's why lead acid batteries probably have a shorter warranty in Phoenix than in Northern Canada. In all honesty, it's mission critical in every application I've seen over the years: military, aerospace, medical. There's a lot of work in the literature on batteries. The only thing you really have to know is V equals I times R. Voltage equals current times resistance. Voltage is the height of the waterfall, current is the amount of water going over the waterfall, and resistance is any implement in the river, rocks, logs, etc. And in all honesty, why should you even build batteries, or should we build batteries? So first year chemistry, or if you're energy or your health and safety official in a plant, they put all reductants in the northeast corner, all oxidants in the southwest corner. The two shall not meet. So how do we manufacture a battery? We put the oxidant here, the reductant here. We separate them by a plastic film that's less than 1/1000th of an inch and 40% porous. So you shouldn't really be doing that. So it's not too much of a surprise that you can have issues if incorrectly manufactured. And then this question, why is lithium? So I don't know if you can see my pointer, but lithium is element 3, okay? The other two are hydrogen and helium. So if you want a light metal, where else do you go? That's the number one reason. Also, it's in the top left-hand corner, which means it gives away its electron really quite easily. So it's small, it's lightweight, and it likes to give out away an electron. That is all about generating electricity. If you look at chemistry, 1 mole of electrons, Avogadro's number, 1 mole of electrons equals 26.8 amp hours. So lithium weighs 7 grams per mole. So in 7 grams, you get 26 amp hours. Nickel weighs almost 10 times that. Lead, 30 times that, even though it's a bit complicated because the lead gives 2 electrons out. But you can see it's lightweight and it likes to give away electrons. Perfect for a battery. Lithium ion was a groundbreaking technology. If you look historically, rechargeable batteries last about 25 years before it's supplanted. So NiCads were invented by, I think it was the German Luftwaffe in World War II. Nickel hydrogen or nickel metal hydride, the next version came about in the 70s. So in the early 90s, lithium ion. But one thing about lithium ion is the chameleon of batteries. Lead acid is pretty well that. Nickel metal hydride is pretty well that. Nickel cadmium is pretty well that. Lithium ion, you can go cobalt, nickel, manganese, aluminum. You can use different negative electrodes, silicon, graphite, lithium titanate. So you can use the whole periodic table with lithium ion. The one thing in common is lithium. So if you're going to bet the farm on a mining venture, pick lithium. That said, that's horse is already bolted out of the stable. So I should have made my fortune previously. The first lithium ion that was implanted was in 2004. Lithium ion was introduced by Sony in 1991, 1992. So about 12 years after the introduction, it was finally implanted. The company was ANS, Advanced Neuromodular Stimulation. And Chris Chavez called it electrochemical pharmaceuticals. So it was for pain management. It was perfect analogy. So you don't take drugs, you take electrochemistry. Lithium ion is the lightest and the best cycle life. It's just a great chemistry. And that's why it's probably going to last more than 20 or 30 years before it's supplanted. We are working on the next generation. The medical industry moves very slowly compared to the commercial. The commercial industry, you know, every year, 3 to 5% improvements in watt hours per liter, which is what the medical industry cares about. That's energy density. They don't care that much about specific energy, which is energy per kilogram, watt hours per kilogram, because the cells are so small anyways. It's the volume that's the key. One of the things that you really got to remember is the batteries are improving 3 to 5% a year. Batteries are evolutionary, not revolutionary. If I was going to spend my $1 million investment, I would improve the electronics and drive the energy use down and use an off-the-shelf battery. Instead of going with a custom battery, you'll have more bang for the bucks for spending your money in the electronics. The applications are all over the place. Pain management is a big one, cochlear implants, monitors, drug pumps, anything is possible with lithium ion. It's just whether you want the patient to recharge it or to be non-tethered, and then you have to use a primary battery. So this shows you Resonetics off-the-shelf cells. Contigo 1.5, it's basically 1.5 milliamp hours. The 3 is 3 milliamp hours, the 20, et cetera, et cetera, et cetera. One thing in common is you can see the blue, that's our first generation cell, the Contigo 50. And then if you look at the Contigo 60, it's the exact same size, 0.88 cc's. All we did was update it with the second generation chemistry, which is, you know, we've got customers that have used the same chemistry for 15 years. So you can't change the chemistry every year, but the commercial people can. So periodically we go in there and update the chemistry, make the packing efficiency a bit better, densify the electrodes, make the separator a bit thinner. And when we do that, you can see that you go from 50 milliamp hours to 65. Again, with the 325, you went from 325 to 440. So the whole key to look is watt hours per liter. So it went from 230 to 280 or 200 to 290. We're also working on the third generation chemistry, and that's going from 325 to 440 to 550. And of course, you can actually give you more capacity in the same volume or give you the same capacity in a smaller volume. So you can see you can go from 6 cc's to 4.8, giving you basically the same performance, 440 versus 420, but it is smaller. So that's where all the drive is nowadays. The biggest drive I see is the energy demands have gone so far down that the batteries are getting smaller and smaller and smaller. And you can see our Contigo 3, which we're just coming out to finishing its development, it's 0.08 cc's. That's not that much bigger than a couple grains of sand, rice. Okay. And this shows you how you can tune performance. Everyone talks about 100% state of charge, and that's not really the way to talk about it. Lithium ion has an organic electrolyte, which means I can change the voltage limit by I can change the capacity by changing the end of charge voltage. If this was a 100 milliamp hour cell, this is a normalized scale. You get 60% of your capacity to 3.8, 77 to 3.9, 82 to 3.95. So just increase the end of charge voltage to a higher and higher limit, you get higher capacity. You can't do that with lead acid. You can't do that with NiCad, and you can't do that with nickel metal hydride because it's got a water-based electrolyte. And once you hit a certain voltage, water just splits. It splits into oxygen and hydrogen. So you can't tune the capacity by changing the end of charge voltage. If you're old enough, you can remember lead acid batteries weren't sealed, and when you were charging them, occasionally there would be an explosion because the hydrogen that was generated would explode. So lithium ion, you can change the capacity based on end of charge voltage. Of course, there's no free lunch. So if we change the end of charge voltage, you can see you get different capacities as was shown on the previous slide, but there is a faster fade in capacity. So I can tune the performance of my cell depending on what you tell me how you're going to use it. So if you want to have 4,000 cycles, I'll charge it to 4.1 volts. But if you want 5,000 or 6,000 cycles, I would charge it to 4.2 volts. So if you want it to last longer and longer and longer, it's best not to take it up to the higher voltages. If you want the cell to last for 20,000 cycles, you're probably only going to charge it to 3.8 volts. Okay. But another aspect is people are looking into charge their batteries faster and faster and faster. C/2 means I charge the capacity in half an hour, or divide an hour in two. C rate means I charge the battery in 1 hour. 2C rate means I charge the battery in 30 minutes. 3C, I charge the battery in a third of an hour. 4C, I charge it in a quarter of an hour. So you can see you take a capacity hit. Ohm's law, V equals I times R. So, but you can charge the battery very fast. But this is maybe not the best representation. You can see it because this is just straight capacity. If we look at it in terms of normalized capacity, you can see that at the C/2 rate, the C rate or the 2C rate, the fade in capacity all overlaps. So I can charge it and have the same fade in capacity at 2C or C/2. I can charge it in 30 minutes or 2 hours and have the same fade. That's in the Contigo 65, which is a stacked plate cell. But if I charge it at 3C or 4C, you can see the fade in capacity is greater. That's because I'm plating lithium on the surface of the negative electrode, and that is getting consumed by interactions with the electrolyte. So it's not really a safety issue. It's not advised, don't get me wrong, because the cell is so small. But if you want to treat your battery properly, you can charge it up to the C/2 rate. And then we also have standard versus standard or Contigo cells versus the custom cells. The Contigo are the ones that I showed you, the Contigo 3, the 1.5, the 20, the 50, the 60, etc. Those are off the shelf and they're qualified. They passed UN transportation and they're ready to go. We have batteries that are qualified in the 440 milliamp hour range to the 50 milliamp hour range. We have a 3 milliamp hour in development. That is going to be finished qualification this year. It's got 0-volt capability. 20 milliamp hour is also in development. That'll be qualified this year. They are all developed and manufactured in ISO 13485, which is the medical quality system, all passed UN transportation. If the cell hasn't passed UN transportation, it's not a cell. You can't ship it. It has to go by ground. So, that is a bare minimum. They've also, some of them have passed IEC, which is another lithium ion requirement. With the off-the-shelf one, there's no NRE required. You might not know whether it'll work for your exact profile, but if we have some cells on the shelf, which we generally do, we can test them under your protocol and prove that the cell will meet your requirements. So there definitely is advantages. Custom cells, they've got the 1 to 2 year lead time. It's a lot of money to get them qualified, and you have to wait for hardware. The supply chain is getting more difficult as we speak. One of the other things good about the Contigo lithium-ion cells is we've got them characterized. This is called DC polarization or DC resistance. I like the DC resistance versus everyone talks about AC impedance. AC impedance is a characterization. DC polarization is how the cell works in a real use environment. So you can look at this graph, and funnily enough, some engineers get excited about these sort of things. You can look at the state of charge, so I know exactly what the state of charge is, and you can follow the resistance. Lithium ion is very flat and then takes off a little bit at the end. So these are the Contigo 1.5, the 50, the 60, and the 65. So we've got all the resistances characterized for all our cell sizes. The next slide, again, the same sort of thing with the Contigo 225, 325, and 440. Okay. So basically, there was an unknown potions master who once said, for those select few who possess the predisposition, I can teach you how to bewitch the mind and ensnare the senses. I can teach you how to bottle fame, brew glory, and put a stopper in death. For me, the battery master, for those select few who can supply me with cycle life requirements, end of life capacity, real-time usage. I can look at our product portfolio and change your usage conditions, basically the charge conditions, voltage and current, to make sure that we give you the best platform for meeting your requirements. And then finally, a known source and inventor once said, the storage battery is, in my opinion, a catch penny, a sensation, a mechanism for swindling the public by stock companies. That's a very famous American inventor. Even back at the turn of the previous century, Thomas Edison saw that people were trying to take your money by promising the world in batteries. If someone promised you 50% improvement in the energy density of the battery in 2 years, they're trying to get your money. They're not going to try to give you a product. I've seen examples in the last 30 years, well, that people have promised great advances in batteries, and some of them will eventually come through, but instead of the 2 to 5 years, it's 20 years. I think it was Fuji initially in like 1995 said they were have a silicone-based negative electrode for lithium-ion cells, and it's going to be commercialized soon. That was 1995. Silicone is now being introduced into the negative electrode in 10, 15%, but that started in 2015. So even a company as big as Fuji took 20 years to realize their promises. So just be careful. That's all I have. So I'll just stop sharing for now and leave it up to Grayson and Rachel to take it from here.
Perfect. Wow. The potions and battery master. That is incredible. I can't claim to be the recharging or power electronics master in the same way as Greg, but really excited to share what we're doing at Resonant Link with Contigo batteries, with Greg and the Resonetics team and beyond. And so we'll keep this short. We'll talk a bit about our mission at Resonant Link. We'll talk a bit about some of the products that we've integrated wireless charging into, and then we'll open it up for Q&A from there. So really, like, how we think about the world at Resonant Link is that non-rechargeable devices kill people and they lower patient quality of life. Right now, if you have a non-rechargeable device and the battery runs out and you need to recharge it, you have surgery. And that has an infection rate. That means we need to have that invasive surgery, and that causes infections, that causes mortality, and that causes a lower patient quality of life. And so instead of this invasive surgery, what we want to do at Resonant Link is we want to make recharging batteries for all implantable active medical devices as simple as just holding up this puck shape that we're showing here on the right for 20 minutes, for 30 minutes, and getting that battery recharge and being able to continue to live your life. So we were launched, now it's been 6 years ago, out of Dartmouth College research and out of Stanford University research, really with the goal of leveraging this breakthrough technology to make patients' lives better. So the fundamental invention that Resonant Link was really launched around and started building around was a much, much improved quality factor for the coils that sit at the heart of a wireless charging system. So instead of using lithium wire or magnet wire, like you might see in most wireless chargers today, we actually have a way to construct these coils using standard off-the-shelf components. They can be biocompatible. That gets about 5 to 10 times lower losses in every single architecture that we build. And that allows us to get deeper implant depths, faster charging, higher efficiency, better alignment tolerance, and smaller device sizes at the end of the day. So we really started there, went and talked to a number of people in the medical device world, and they wanted end-to-end amazing wireless chargers, not just coils. And so we've really built out this suite of technology that allows us to deliver great wireless charging experience across a bunch of different device sizes, platforms, indications, and power levels. So the other things that we've really focused on are novel shielding and a really deep understanding of electromagnetics that let us integrate wireless charging near batteries like Resonetics Contigo lineup, near electronics, near titanium cans, and always in a medical device, we're surrounded by different types of tissue that have different electromagnetic characteristics and different thermal characteristics. So we focused a ton there, the place that we can drive a lot of value in your devices. My PhD is actually in megahertz frequency power electronics. So we've got great inverters and rectifiers as pieces of the system. And then the other thing that we heard from a lot of people was that it's hard to get data in and out of the body. And so we have a proprietary communication scheme that allows us to send bidirectional data through the wireless link at over 100 kilobits per second. And that enables our customers to get rid of Bluetooth links, to get rid of RF links, or have lower bandwidth other communication channels, and is really powerful. And we can integrate wireless charging and that data into a single link there. So we've taken that technology suite and we've really applied it across a number of different power levels and sizes. We've gone all the way from, now we have a 2 milliwatt customer application, all the way up to 20, 30, 40 watts. And that means that we can serve really any device on the market that needs different characteristics and different recharging. Some of our customers really want to optimize the time to recharge. Others are really, really focused on how miniaturized we can make that implant. And others are looking at that data communication or off-the-shelf fabrication techniques or misalignment tolerance to make it really easy for patients to recharge. All of those are things that we can help you achieve with wireless charging for the device. So everything from this 3 millimeter, 10 milliwatt range device up to devices that can power ventricular assist devices, pumps, and beyond. All of that is something that we've built before, that's proven with customers, and that we're ready to scale from proven platforms. The one platform I really want to focus on today is the one that we co-developed with the Resonetics team, and that is a 21-minute recharge for devices integrated into titanium cans. So we really designed this for things like cardiac rhythm management, for neurostimulators like SCS, DBS, sacral nerve devices. Really anything that's inside a titanium can, we can get that charging time with a proven platform down to 21 minutes. And for patients that recharge daily, for patients that recharge weekly, that's saving them days a year. And we're fitting that recharge time into a Netflix episode or into the nightly news, instead of it being a 4-hour recharge time that really interrupts their lives. The other things that we focus on with this platform are really strong misalignment and implant depth specifications, so you can serve all patients, and it's much simpler to integrate this with patients' lives and not have that real big frustration with getting that alignment right. The other thing that we have is part of that fast data channel is that we have a really fast control loop on our chargers. And that means that patients can move around while they're charging. They can walk, they can take the dog out, they can cook, they can move around their house, or continue to live their lives during this very fast recharge time. So this is an off-the-shelf platform, shipping it to customers to play with and to integrate with a very quick customization process based on this proven platform. And really where we partnered with Resonetics here is on that battery that's inside the implant. So this one, we're charging a Contigo 440 battery from 20 to 80% SOC in 21 minutes. And the combination of what Resonant Link can do on the recharging side and what Resonetics can do on the battery side gives us really, really powerful patient experience. We're #1 in charging for medical devices. We've got over 30 OEM partners. Again, we have this broad sweep from 10 milliwatts all the way up to tens of watts. I'm still on audio, but I did lose power at our house, and I'll be back online shortly.
No worries. I think it was, if it was going to happen, it was perfect timing since you were kind of at the end of your slides. And I know we already have some questions coming in from the audience, so we'll just go with audio for the rest of this. So just a reminder for everyone, if you have a question, please drop it into the Q&A feature in Zoom. It should be at the bottom of your screen and kind of that toolbar. And again, if we run out of time, we will follow up with you directly with an answer to your question, but we should have lots of questions we're able to answer. So first one is for you, Greg. An attendee asked, is there any special qualification process that's required for implantable batteries in comparison with other industries such as industrial batteries?
We used to manufacture military batteries, and they were like 2.5 inches by 4.5 inches by 5 inches, and we sold them for $100. Now we're selling you something that's 1 centimeter by 2 centimeters by 3 centimeters, and we're selling it for $400. What you don't see is the pile of paperwork that backs the medical battery that does not back the defense-based battery. Every cell we manufacture has a unique serial number. I can trace how much electrolyte I put into the cell. I can trace how much active cathode material, how much negative electrode material. I have 100% traceability. It's also the documentation. It's not that in the industrial setting you don't validate your processes, but I mean, it's the documentation is far more rigorous in the medical system. We do IQ, OQ, and PQ, installation qualification, operational qualification, performance qualification. We do a PPQ, so we build 3 cell slots, then we analyze them by SQC. They have to have a CPK of 1.33, so it goes on and on and on. So we follow an ISO 13485. We get audited, so it's the more rigors and it's the documentation that you can use as backdrop. If we do have an issue, we keep retention samples for years. We cycle 1 cell from every lot. So it's just the document package you do not see, but you can access.
That's great. Very thorough. Thank you. This question is for Grayson. Can you talk about the applications for continuous wireless power a bit more? You talked about recharging quite a bit, but you can also power devices wirelessly without having an implanted battery. Is that correct? And what are the kind of applications that you see that used for and the benefits of that?
Absolutely, yeah. So we do both recharging of batteries and continuous power devices, and we have seen a lot of success with customers that are in the continuous power space with that really fast control loop that gives really reliable wireless power there. So actually, some of our customers like Paradromics is one that's on our website that you can read about, thought they needed an implant battery basically for those short interruptions in operation that would occur with most wireless chargers. And with the uptime, with the reliability, and with the robustness of Resonant Link's wireless charging or wireless power in this use case, they could actually completely get rid of that implant battery, which shortens the regulatory timeline, makes their device much smaller, much easier to implant. And we can provide that continuous power in a really reliable manner. So we love doing wireless recharging. We also love doing wireless power for continuous power applications. And both of those are things that we've done with a number of different partners to date.
Awesome. Thank you so much. So we have lots more questions coming in. So thank you all. We will do our best to get to all of them. So Grayson, this one's for you as well. On one slide, you showed implants with different power needs, the 20 milliwatts to 10 watts. Are those power numbers power delivered to the implant or charger output power?
Those numbers are power delivered to the implant. So we don't usually talk about the input power because that's not ultimately what the implant can use at the end of the day. So those numbers are power that we deliver to the implant at the output of that wireless charging system.
Awesome. Thank you. Lots of questions coming in about implant depth for wireless charging. So some more questions for you, Grayson. Can you talk about the maximum distance between the charger and the implant, and then how that varies for the smallest applications and smaller antennas for, I'm guessing, somebody's thinking about device miniaturization?
We can do all sorts of implant depth. We've done everything from devices that we know will be very near the surface of the skin, 1 or 2 centimeters, all the way to ones that are implanted deep inside the torso. I believe the deepest implant depth we've done is 10 centimeters. And typically it's something that we'll work with customers when we do that customization, know exactly what they're aiming for, right? Deeper implant depth for most standard devices really lets you serve more patients, and more patients can use your device. So it's something that's super important. We've designed the platform to be at that 4 centimeter implant depth. But when we go to that customization stage, sometimes people are looking for more, sometimes people are looking for less, and we can update the design to meet those needs there.
Awesome. Thanks for that. This next question, this is for Gregg. So Gregg, how you talked about this a little bit, but how does cycle life hold up with fast recharging? And how does a customer, like, how would you work with a customer to understand sort of the best C rate or best recharge time frame for that battery, or vice versa?
Most of that depends on the chemistry, and you can't avoid that, but this is where the mechanical engineering or the cell design comes in. If you looked at, we can supply data sheets and all that. If you looked at some of the cells, they're in square cans or they're in D-shaped. So you can make them in a jelly roll, which has 1 positive electrode and 1 negative electrode, and you wind them up just like a cylindrical cell, but you put them in a square can or elliptical can. So those are wound cells. In a D shape, you can't wind it. You have to have stacked plates, so you have different number of electrodes. For like the Contigo 440, you've got 2 tabs or 2 connections to the outside world. For the Contigo 65, we have 23 tabs. So it's all about the distance the electron has to travel. You make it as short as possible. So if you want a fast charge, we'd probably go with a stacked plate design. Like I said, and we show you can do it at 2C. You can even do it a bit higher rate. You could probably do it at 3C, but then you'd have to tune the voltage a bit, because you saw Grayson fast charging it from 20% to 80%. And that's what all the EVs are doing. So you tune the cell design for high rate capability, and then you tune your charge regime. It's going from 20% or 0% state of charge to 100% state of charge, where you can start causing damage to the electrodes. So you just stop it at 3.9 volts. So it's tuning the cell design for high rate capability, and then tuning the charge regime to give you what you want.
Perfect. Thank you. We have a couple of questions about safety coming in. So this first one will be for Grayson, and then we'll go back to Gregg. Grayson, a couple of people have asked about temperature. They've asked, is there a concern of overheating at the implant during charging? And then, is charging through tissue considered an induction process? Is there heat generated that can harm tissue? So just kind of addressing that, if you will, more broadly. Thanks.
Yeah, absolutely. So we always design to be under the safe limits that are defined by the FDA for both SAR of tissue and for heating of tissue, which combines electromagnetics, the heating that occurs during charging, the heating that might occur during the delivery of the treatment. And we're always under those limits. So the titanium can platform that we showcase was designed for the 2Chem 43 standard. And I think we came in even below that. So our temperature rise at 2.5 watts of charging is about 1.5 degrees C there. And that is well below the FDA temperature limits. That's well below that 2Chem 43 standard. And so we always make sure that we comply with those, and different partners have different standards they want to comply with. It's easy for us to design around. We've built our own biopower tool, we call it, which is an analytical package to make those easy updates to comply with different standards or have different customization needs there. And so we make sure that the wireless charging is safe for all different implant conditions and for all different states of play of where that device might be operating.
Awesome. Thanks for that. Greg, we're going to turn to you, and this is sort of related to safety a little broader. Can you share both some examples of implantable batteries that you've used, and then also, you touched on this in the webinar a bit, but the risks involved and how you've mitigated some of the risks?
So, I mean, the biggest cell that we've implanted is 440 milliamp hours. Safety and size go hand in hand. The larger the cell, the more the safety risk. It's as simple as that. The 440, 100% of our cells are designed with something called a shutdown separator. It's a tri-layer. It's that separates the positive electrode and the negative electrode. And if it gets too hot, it's a layer of polyethylene between two layers of polypropylene. Polyethylene has a different melting point than polypropylene. So if it gets to 135 degrees C, which is quite toasty, but don't forget it starts right in the internal of the cell, the separator, the polyethylene melts and it closes the pores, and the polypropylene holds the mechanical integrity because you don't want the separator shrinking. So these are for a hard short. I mean, really hard short. So 100% of our cells are designed to have zero external safety features and still be safe during a short circuit event. On top of that, then you've got something called the BMS, Battery Management System, and that is what our customers or Grayson can help. Stops overcharge, over discharge, stops the rate. So I mean, it's electronics that protect the cell so that if you design it to stop charging at 4.1, it stops charging at 4.1. If the battery wants to discharge at too high a rate, the electronics controls that. So you've got internal protections and you've got external protections. On top of that, the 440 is the biggest cell we manufacture. As the medical cells are getting smaller and smaller and smaller, the safety goes up. I don't think you can make a Contigo 3 have a safety event no matter what you do, because it's so small, it doesn't have enough energy to cause anything, and it dissipates all its heat. What you have the biggest problems with in safety is when you've got a very large battery with multiple cells in it that are insulated and they heat up one another, and it's basically self-heating. And that's what thermal runaway is. You can't stop the reaction from a safety event because once it reaches a point, you can't dissipate the heat. With small single cell batteries, that is not an issue. You can easily dissipate the heat. They have safety features in them, and they don't have enough energy to cause an issue.
Awesome. Thank you, Greg. Next question for you, Grayson. 2 questions. What is your frequency for your charging? And then also, has there been any work on a multi-coil charger array to enable even more alignment forgiveness? And what would be the trade-offs and considerations with that?
Absolutely, yeah. So we've done frequencies from tens of kilohertz all the way to tens of megahertz. Sometimes customers have very specific targets or constraints, and so we've designed at all sorts of frequencies. Our most common and the platform that we built operate at 6.78 megahertz in that international band that's allocated for radiators like wireless chargers. So we usually recommend 6.78 megahertz, but we've worked across all different frequencies. And then we have done some work on multi-coil arrays. We have worked with partners that just have huge needs on misalignment or on where the device might be, and those are sometimes best served by multi-coil arrays. So most of our applications are single coils. Others, we're happy to do multi-coil, and that's a place that we can look at the customization there.
Awesome. Thanks for that. Next question, and just a reminder, attendees can keep dropping questions in. They've been coming pretty consistently. So just use the Q&A feature if you joined late or if you have additional questions. So this is for you, Greg. An attendee asked, how do you see the solid state battery technology or solid state batteries entering the implantable market?
A very complex question. And I mean, what do you mean by solid state? Because there's different beasts in the market, or potentially beasts in the market. There is lithium ion, where they've got a negative electrode in the standard solid state where the lithium gets charged into the graphite or the silicone. And then there's metallic lithium, which is the holy grail. And I started my career on metallic lithium. And I have real safety hesitations with metallic lithium. I think everyone is underestimating the time that's going to take to develop that technology. As I said, Fuji took 20 years to introduce theirs. Metallic lithium is going to be a real problem because you're trying to change the spots on a leopard. Like I say, you get the chemistry right, you're fine. If you get the chemistry wrong, it doesn't matter what cell size, you can do the mechanical engineering. I think that the reason I say it, I'd say it's 8 to 10 years ago away. And the reason I say that is all the interest I've seen in solid polymer is smaller and smaller cells. All the interest in the commercial market is bigger and bigger cells. And that's all for the EVs. If someone could make a large cell with a solid polymer, they'd be talking about it. So I think they're making the smaller cells because they're worried of the safety aspect. So I think you've got, I'll be long since retired before it is introduced commercially. But I think medical is the niche where it's going to start because it is small size. But I think because they're focusing on the small size and not the large size, there's technical issues that they've come against and they're kind of avoiding them. So I'm the grumpy old man.
Well, I like the leopards and spots analogy. So thanks, Greg. Next question that's come in. This one's for you, Grayson. A couple of really specific questions. How is the charger typically mounted to the patient?
Yeah, so typically our partners will want to control that patient experience side. So vest, belt, sometimes it's a little handheld device, and we will work some, we've done skull caps for devices that are implanted in the brain, other creative solutions that our partners have come up with. Typically they'll own that patient experience and sort of user interface side, and then we'll focus on the core wireless charging piece.
Awesome. Now, a couple more questions for you, Grayson. In the titanium can application, is the receiving antenna enclosed in the titanium can or in a header outside of the can?
In our off-the-shelf platform, it is enclosed in the header there. So it's basically the coil is around the terminals for where the leads would connect. And then we've also worked with customers that want that integrated into the can. And so we've done that before and are happy to provide that. But the standard platform is the coil is integrated into the header.
Awesome. We also have a question about VADs. For VADs that take up much of the juice, for example, 5 watts to 8 watts, how do you see wireless charging technology would be applied in these devices?
Yeah, so we have worked on ventricular assist devices for a long time now, and what we've seen is that the Resonant Link MSRS coil technology really enables the delivery of 5, 10, 20 watts into the body while staying below the FDA temperature limits in a really unique and first of its kind way. And so I know there's a big push right now to reduce the ventricular assist device power consumption down to that 5 to 10 watt range and maybe even lower that some people are going after. And we are really happy to provide transcutaneous energy transfer TET solutions, it's often called there, for anything from that 2 watt, 5 watt, 10 watt, all the way up to 20, 30, 40 watts. And we can do all of that with best in class size, best in class implant depth, best in class misalignment while staying below those FDA temperature limits.
Awesome. Thanks for that. A couple more questions have come in for you, Grayson. So one, this attendee says, maybe this is a question for Medtronic, and the next time if a patient has a device that needs to be replaced because it has a primary cell battery, will they be able to replace it with wireless recharging in the future? Or have you talked to any customers about how that process would look?
We would love to make that happen. And we're working with partners to make every device rechargeable in the next decade. And that has to include backward compatibility with primary cell implants.
Awesome. So we just have a few more minutes. So again, attendees, if you have additional questions that haven't been answered, kind of last call to drop them into the Q&A feature in Zoom, and we will do our best to squeeze them in. One question for both Greg and Grayson. We'll start with you, Greg. You talked about size quite a bit. Can you just mention what's the smallest battery that you've implanted, and then also had on kind of an external, either a transmitter or a wearable application?
Okay, well, the smallest one that will be implanted is 0.08 cc's. That's the Contigo 3. We have developed one, or partially developed one, that is 0.05 cc's. So sorry for the American audience, we do use metric in Canada.
No, that's great. I think CC is great. Can you give the audience a sense of kind of dimensions as well of those batteries?
Okay, let's just go to my handy dandy notebook.
Making you do math on the spot.
So for both of these cells are small cylindrical cells. So for the 0.08 cc's, it's 2.9 millimeters in diameter and 12 millimeters in length. Since there comes a limit on the ability to get something into a small size, because you're always going to have void volume, so your energy efficiency or energy density goes up as volume goes up and goes down as volume goes down. So the one that's half the capacity is far greater than half the size. So the smallest one, which is about 1.2 milliamp hours, is 2.9 millimeters in diameter by about 8 millimeters in length. And I think we are looking at even smaller, but then again, you've got to start thinking about different manufacturing techniques.
Perfect. That's very helpful. Thank you. And then Grayson, same question to you. How small are the smallest wireless chargers you built? And is it just on the implant side or also on the external side?
Yeah, so the implant side is typically where people are trying to really, really reduce size. And I think we shown that 3 millimeter diameter one in the slides. We actually have one that's under 2 millimeters in diameter on the implant as well. That is a partnership that we're working on right now. So we can get them very, very small, and the MSRS technology, the coil technology, really shines even more as we push the limits of what's possible there. So we can shrink the implant side down. We can also make the external, or the outside the body transmitter lighter, smaller, whatever people are pushing for. But we typically see people trying to miniaturize that implant first.
Awesome. That's great. Thank you all. Well, we are just about at time. So I want to thank Gregg Bruce and Grayson Zulauf for the wealth of information you've shared with us today. And thank you all for attending our webinar on next generation batteries and charging. You'll receive a recording within the next day or so. I hope you have a lovely afternoon. Thank you all.